Hello everyone, how's it going? Hope you're all doing okay. I want to do this video on this idea I had about finding the Laplace inverse of the Riemann Zeta function of, uh, of, uh, of S. And spoiler alert, it can't actually be done directly, but there's kind of a way of talking about something similar that relates to it from this really interesting result involving the floor function and having to do a telescoping series, and it's pretty interesting. I wanted to share that with you. So this is basically what we're after, Laplace inverse of zeta of S. Now, if you don't know what these things mean, I'll kind of describe as we go along. But zeta of S, if you're curious, is first defined as the sum from n equals 1 to infinity of 1 over n to the s. So if you've taken Calculus 2 before, this should remind you of P series, for example. Here, S is a complex number, and there's a little more to it as far as what S is. And if S is a real part that's bigger than 1, then that series definition is true. And if not, then you have to kind of extend it to other ways of defining zeta such that that also holds. But I digress. Okay, so instead of starting with this directly, what I will do is I'll actually start off with interesting property of the floor function. And if you don't know what the floor function is, these are the notation, kind of like these half brackets that are on the bottom. And basically, if you take the floor function of any real number, it rounds down to the nearest integer. So for example, what is the floor function of pi? Well, pi is 3 point something, 3.14159 or whatever, but it rounds down to 3. The nearest integer below that is 3, so it rounds down to 3. So that's all the floor function does. It's a rounding down function. Okay, so with that out of the way, well, let's consider the following property. If you have the integral from 1 to infinity of the floor function of t times any function of t dt, what happens? Well, as it turns out, you can rewrite this as the sum from n equals 1 to infinity of the integral from n to n plus 1 of the floor of t times f of t. Now, what's really nice here is that since the integral is in between two consecutive integer values, assuming n and n plus 1 are integer values, of course, then the floor function of t is just the smaller one. It rounds down to the nearest integer, which if t is any value between n and n plus 1, then of course the floor will round down to n. Okay. So the floor of t is just n, and n is independent of t, so you can pull that out of the integral, so you end up getting this basically. Okay. Now I don't know anything about what f is, but let's just say its antiderivative is called capital F. So by the fundamental theorem of calculus, what do we have? We have the antiderivative evaluated between the limits subtracted. So we have capital F of the top limit minus capital F of the bottom limit. Perfect. So now what this really reminds me of is a telescoping series. So I'm going to actually try to explain a little bit what that is. It's not terribly hard to understand. If you have the sum from n equals 1 to, let's say, capital N of a sequence a sub n plus 1 minus a sub n, well, what ends up happening is when you plug in n to be 1, 2, 3, and so on, you can kind of see, if you try it on your own, you get a sub 2 minus a sub 1 plus a sub 3 minus a sub 2, so the a2's will cancel. And if you keep doing this, the a3's will cancel, the a4's will cancel, it'll keep canceling forever. Now, the first negative a1 did not cancel, and if you go to infinity, well, really, if you go to capital N, the first part here, when you plug in a sub n plus 1, that will not cancel with anything because it's the last of the highest values, basically. So what this ends up turning into, after all the telescoping cancellation collapses, basically, you end up getting a sub n plus 1 minus a sub 1. Basically plugging in the top limit into the first part of the subtraction and the bottom limit into the second part of the subtraction. Now, of course, as n goes towards infinity, well, we would like this to tend towards 0. Now, in reality, it can tend towards any constant value, but we'll see that we'll end up considering the ones that go to 0 for what we care to talk about here. Okay, now, to make this look exactly like, this doesn't look exactly like that, but to make it look exactly like that, I want this n to be an n plus 1 for this distribution and just an n for that distribution. So how the heck does that work out? So it's a little hard to see maybe, but I'll distribute this. And what I want to get is I want this. Check this out. So I want an n plus 1 times capital F of n plus 1 minus n times capital F of n. Now that second part of subtraction I have from that distribution, that's fine. But this I don't quite have. Now notice if you distribute this actually back into these two, well, one of them we do have. This first part actually we have from that distribution up there. But then because we don't have the second one, guess what? We have to actually subtract that off. Now I will subtract it off in its own sum off to the side, and I will assume capital F is such that that sum converges absolutely, so we can do this separation of sums like that. So we need capital F of n plus 1. And if you try this on your own to kind of combine them back together, you will see after you distribute that capital F into n and n plus 1, everything cancels out in a nice way and it gives you back the previous line. So this does work out. I'm not pulling a fast one on you. Okay, great. Now what? Well, so now, this is indeed telescoping. This is a sub n plus 1, this is a sub n, and we're taking the sum of this whole thing like that. So in fact, by telescoping series, what we end up getting is a sub 1, which is really, this is a sub n. So when you plug in 1, you get f of 1. What is f of 1 though? Well, we'll worry about what that is in a bit. But right now, let's just say we get negative 1 times f of 1, so I'll just write it like that. Okay, minus the sum from n equals 1 to infinity of f of n plus 1. I'll actually reindex this. And a nice way to reindex is you kind of imagine balancing. So whatever you do to the beginning value of the infinite sum, you do the opposite to all the ends inside of the sum end. So if I increase this to 2, I have to decrease all of the ends on the inside by 1. Now notice n plus 1 minus 1 is just n, so this becomes f of n like that. Now these combine to negative the sum from n equals 1 to infinity of capital F of n, because of course this sum is from 2 to infinity and this is the first one. So combining them, you go from 1 to infinity basically. And what we really, really want is we want this to be zeta of s. Now zeta of s, remember, is the sum from n equals 1 to infinity of 1 over n to the s. So to make that the case, of course, this must be negative n to the negative s, because double negative is positive, so that negative will cancel with the negative that I've just constructed there. Perfect. So we have a nice result. Kind of. We have capital F of n. All right, I'll replace n with t. Trying to think if we used, well, we kind of didn't use a capital F of t, but it's an antiderivative of lowercase f of t, so it's okay. So capital F of t, we want to be negative t to the negative s so that that works out. And since lowercase f is the derivative of this, then if you take the derivative, you get, well, the negative s comes down, so you get s to the s times t to the negative s minus 4. Perfect. And now if you plug this back into the original integral, we get the following result. We get the integral from 1 to infinity of the floor of t times this function, which is s times t to the negative s minus 1 dt, is equal to zeta of s. Perfect. And now what I'm going to do is manipulate that integral to make it look like Laplace of something. Now, I mentioned Laplace at the beginning, but what is Laplace? If you don't know, Laplace is defined to be this. So we're going to write this kind of cursive L in of braces. Inside the braces we have a function f of t, and it's defined to be the integral from 0 to infinity of that function of t multiplied by e to the negative st dt. That is how you define Laplace. That is how Laplace of something is defined. Okay. Now what's really going on here is Laplace takes in a function of t and outputs a function of s. Notice here s is a new variable basically. T is the dummy variable in this case because we're integrating with respect to t. So that'll go away in the end. For example, Laplace of t to the 1, or yeah, just t basically, ends up being 1 over s squared. So the Laplace inverse of 1 over s squared gives you back that t. So that's what we're trying to do here is take the Laplace inverse of the Riemann Zeta function of s and see what function of t you would need to plug into Laplace to get that back. So that's kind of the idea we're trying to answer. That question we're trying to answer, kind of. Okay, so to make this work out, what I'm going to notice is that if this t was e to the u, then we have e to the u to the negative s, which is e to the negative su, which looks very much like this e to the negative st. Okay, so to make that the case, I will apply the substitution that t is equal to e to the u. So the dt, notice, is e to the u du, and things are going to work out really, really, really nicely, I think. Let's take a look. So our integral turns into, let's take a look at the limits. So if t is 1, e to the what is 1? E to the 0 is 1, so the bottom limit is 0 now. Perfect. And that lines up with Laplace, so I'm really happy with that. Similarly, e to the infinity is infinity, so that works out really nicely as well. The s that's multiplied right here, I'll actually pull that out of the integral. I'm not too worried about that because it doesn't involve t. Now notice where we do want to involve s is in the power of e, so we already kind of figured that out, so that'll be okay. Now t is e to the u, so we get that inside the floor, and now we have t to the negative s minus 1. Now remember, that's e to the negative, I'll write it as negative s times u, because it's really e to the u to the negative s, which is e to the negative su, and then we have still a minus 1 there. So that's t to the negative, times t to the negative 1, but t is negative e to the u, so that's e to the negative u. Good. And now the dt is e to the u, I meant to put du here, not dt, so sorry about that. Yeah, there we go. And now notice these e to the u's actually cancel out, which is really, really nice, and we're done. We're like literally done. Why is that? Well, now if we do one more substitution, the kind of trivial substitution u is equal to t, we end up getting that, well, we actually have Laplace of something, kind of. So replacing those u's back with t's, this is s times Laplace of the floor of e to the t. Look at that. Perfect. So we have shown the following result. That if you take Laplace of the floor of e to the t, you will, believe it or not, get zeta of s over s. Now I mentioned a little bit about the real part of s being bigger than 1. In fact, this has to be the case here. If the real part of s is not bigger than 1, you can actually use the summation definition of the Riemann Zeta function. I actually have a video that I've done previously, kind of similar in flavor to this, where we take a look at the Malin transform instead of Laplace transform. Malin transform is a little different, of something that gives you something to do with Laplace. In that case, and I'll link the video here, you'll actually get a different kind of domain change, and it's valid for other values of s where the real part of s is actually between 0 and 1, which is very, very interesting if you're curious or interested in solving something like the Riemann hypothesis, which has to do when the real part of s is in between 0 and 1. So it's very, very notable. Okay, so that's where I'm going to end this video. Hope you all enjoyed. If you have any questions or concerns, please comment below. I'd love to see your thoughts. If you enjoyed this video, please like and subscribe if you're not subscribed already, and I'll see you in the next video. Thanks for watching.